Okay, so just some general housekeeping items to begin with. At the end of this week, on I guess Tuesday, not the end of this week, but tomorrow, we're going to be doing Lab 3. Read through that a little bit before you come. It's over the scientific method, how to develop hypotheses, and then we're going to be going over some statistical tests. So we'll have you guys calculate what's called a student's t-test. So there'll be a little bit of math. If you would like, please bring your own calculator, if you're comfortable with one. And then there will be a quiz posted Thursday, and that will cover whatever we cover Monday and Wednesday, so today and Wednesday in lecture, and then also Chapter 2 in the Elephants on Acid book. Okay. And then next week, on Wednesday, we're going to have our first exam. And the syllabus says that we should be all the way done with Chapter 4 by then, but I don't think that we will be. My guess is we're going to get through all of Chapter 3, and then we might start a little bit of Chapter 4. But whatever we get through by next Monday will be what we cover on the exam. And it will only be lecture content. There won't be any Elephants on Acid on the exam. Okay, any questions about that? So my intention is to end a little bit early Monday next, so that we can have a little bit of a review, go over anything that still isn't very clear to you all. Okay? So today what we're going to do is start Chapter 2, and this is kind of all the chemistry that you're going to need for the rest of the semester. So chemistry is just a study of the properties of substances. And really, they study first substances at their fundamental level, like at the atomic level. And chemists are interested with how it is that atoms interact to form larger, more complex structures, and what kind of physical properties are associated with those. Now, most all things that we're familiar with are classified as matter, and matter is defined as anything that occupies some space and has some mass. And mass is just a measure of weight, right? So anything that's matter, we ought to be able to put on some sort of scale and measure how much it weighs. Can y'all think of anything that doesn't fit those criteria, that doesn't occupy some space and doesn't have some mass? Can you think of anything? Yeah.
Gases count?
Okay, I appreciate that you brought up gases. In fact, gases have some mass, and we can actually measure that a little bit. Like if you were to take a tire that was completely deflated and you were to inflate it, you'd actually feel it becoming heavier. And the reason for that is gas consists of atoms, and atoms have some mass. And when you compress air into a tire, you're taking atoms and you're squishing them really close together and shoving a whole bunch of them in there. And so gas is a common gas, but in actuality that's considered matter because it actually does have some mass and can occupy space. Can you think of anything else? Yeah, what do you think?
Would it be water?
Water is another really good example, liquids. But liquids, like gases, consist of atoms. And so you can take water, right? And you can put it on a scale and it would actually weigh something more than just the glass that's containing it. Are there others? You guys have really stopped to consider what the internet actually is. So what is the internet? Other than like Big Brother watching us all the time. And it really is. I mean, it really is that. But besides that, we can talk about internet security and stuff like that some other time. So in a previous life, I worked for an e-commerce company, and my job was search engine optimization. So what I did was I designed websites that would rank really, really high on Google's search engine results page, so that whether or not that's really what you wanted to see, we led you to believe that that's what you wanted to see. It was really insidious. But it's neither here nor there. What is the internet?
Just like energy?
Yeah, exactly. It's information stored as energy, right? I mean, it's just this huge network of information. So you can go to Google, and you can ask the Google about, like, I don't know, cow milk, and there'll just be a whole bunch of information that's dumped on you for cow milk. But it's just information, right? It's just knowledge. We can kind of store that knowledge, and the stuff that we store that knowledge in occupies some space, but the actual knowledge doesn't really. I mean, it's just kind of this ambiguous sort of thing that doesn't really have mass or occupy a real physical space. So information is a really good example of something that isn't matter. Most everything else consists of matter. Now, the fundamental unit of matter is an atom. And an atom is important because atoms have some chemical property and some physical property. And really, it's the smallest unit of organization that is able to retain some standard chemical property or physical property. Now, let me explain to you what I mean. If you were to take two carbon atoms and you were to stick them together, those two carbon atoms would have the same chemical and physical properties as a single carbon atom. Likewise, if you were to take a whole bunch of oxygen and squish it all together, all of those oxygen atoms would have the exact same chemical properties as just a single oxygen atom. But if you were to take that single oxygen atom and start tearing stuff off of it, like protons or neutrons or electrons, we're going to change the properties of that atom. So the atom is important because it is the fundamental unit of organization that retains some important physical or chemical properties. Now we know that atoms have specific parts, right? And there are protons, which are positively charged particles that exist at the nucleus of an atom. There are neutrons that carry what kind of a charge? It's close to negative. It's neutral. I know I like to throw that curveball at people. It's a neutrally charged particle, right? So we have protons and neutrons in the nucleus, positive and neutrally charged particles. And then we have little electrons that float around an atom, right? And those are negatively charged, right? Okay. So those are the three constituents of an atom. Now, I don't have this on the PowerPoint, but I would like you to keep this in mind. When naturally occurring, the number of protons is equal to the number of electrons. Neutrons are wacky. There can be any number of neutrons. But generally speaking, when naturally occurring, and particularly without a charge, the number of protons is equal to the number of electrons. Now there are specific ways that we can classify atoms. And there's a periodic table right over there on the side of the wall, and you'll notice that that periodic table of elements is organized primarily by some letters, right? Each of those elements has some atomic symbol. And that atomic symbol is one or two letters. And those one or two letters are derived from either the Latin or the English name for that element. For example, carbon has the atomic symbol of C. Oxygen has the atomic symbol of O. Silver has the atomic symbol of Ag. And then potassium has the atomic symbol of K. So if you see C in an atomic equation, or excuse me, a molecular equation, it's always going to represent carbon. O will always represent oxygen. Now each of these elements have a specific number of component parts. The most important, in fact, the defining characteristic of an element is the number of protons, and that's called the atomic number. So if you were to look at that periodic table, what you would see is the element C, carbon, and then it has a number up above it. And the relative position of that number will vary depending on who's writing the numbers and the letters. But what that means is the atomic number 6 means that carbon has 6 protons. And that is going to be constant across all carbon atoms. All carbon atoms have 6 protons. In fact, you could say it inverse of that. Any atom that only has 6 protons is a carbon atom. And all elements follow that pattern. So nitrogen, for example, has an atomic number of 7, which means that it has 7 protons. If something happens to carbon and it picks up another proton, it's no longer carbon. All of a sudden, it's nitrogen. Oxygen has an atomic number of 8, and that will always be so. There's also something called the atomic mass. And the atomic mass is the sum total of all protons and neutrons. What that's really saying is, if we want to measure how much an atom weighs, the two important particles are the protons and the neutrons. Electrons, we know they exist, but they don't really contribute very much to mass. In fact, an extremely negligible amount. So really, if we want to weigh an atom, we're going to weigh the protons and the neutrons. Generally speaking, the atomic mass is given below the atomic symbol. So if we were to round to the closest whole number, the atomic mass of carbon is 12. So given what you know about atomic mass and atomic number, how many neutrons does that atom have? 6, right? Because atomic mass is the number of protons, which is 6, plus neutrons. And both of those two things have to sum to 12. Okay, so oxygen also has an atomic mass of 8, not also, but it has an atomic number of 8, and it has an atomic mass of 16. So it has how many protons, or excuse me, how many neutrons?
8.
8 as well. Silver is a little bit different. Like, this is cool when you get the same number of protons and neutrons, but that's not always the case. Silver, which is Ag, has an atomic number of 47 and an atomic mass of 108. So first of all, how many protons does it have? 47. Second, how many neutrons does it have?
51.
It's close to 51. 61, right? Yeah, it has 61 protons, or excuse me, neutrons. Because if we add 61 to that, we're going to get 108, right? Okay. Now, as I said earlier, generally speaking, if there isn't a charge associated with either of those atomic symbols, what that means is there are an equal number of protons and electrons. So if carbon doesn't carry a charge and it has 6 protons, that means it also has 6 electrons. Our electrons are organized into things called shells. And if you take chemistry, and I hope that you do, because then you're really going to realize how cool biology is, the chemists will talk about different kinds of electron orbits. There are p orbits, and there are s orbits, and r orbits, and all sorts of wacky stuff. And those are kind of illustrated here on this little poster. But when we consider electrons and electron orbits, we're going to consider them as concentric rings around an atom. And it's really the simplest way for us to visualize what an atom looks like. So, and I'm just going to draw some ambiguous atom here on the board. I'm going to draw a nucleus, and that nucleus consists of some number of protons and some number of neutrons. And then electrons are going to organize in concentric rings about that nucleus. Now, the first ring around, or electron orbit, around an atom can hold up to 2 electrons. So if I was to draw that, I would draw 2 little dots like that, and then a circle around. In the next orbit, we can have up to 8 electrons. So the next orbit would have up to 8 electrons. Likewise, the third orbit can hold up to 8 electrons. Like so. And for our purposes, we're never going to diagram or really consider very many atoms that have, or at least be concerned with the chemical structure of very many atoms that have more than that many electrons. Okay? Now, if you go out a little bit farther, the number of potential electrons increases. So the fourth shell can hold 18 electrons, the fifth shell can hold 18 electrons, and then you just kind of increase the number of electrons as you move out from the nucleus. One of the important characteristics associated with electrons relative to the nucleus is their distance. The farther an electron is from the nucleus, the more energy that represents. And energy accounting is going to be incredibly important for us, particularly when we start talking about like photosynthesis. Because with photosynthesis, plants start monkeying around with where electrons are located, increasing the energy and allowing that energy to be released and picked up by other molecules. So the farther from the nucleus, the more energy it represents. What that means is, relative to this electron right here, this one carries less energy and is perhaps a little bit less valuable to the biological system that it finds itself in. Okay? Now what we can do is we can take our chemical number, or excuse me, our atomic number and our atomic mass, and we can actually diagram atoms. It's very common for me to have you diagram an atom on the exam, so I'd like you to be pretty comfortable with this. Let's diagram carbon. So carbon has an atomic number of 6 and an atomic mass of 12. What that means is, in the nucleus, it has some number of protons and it has some number of neutrons, right? So carbon has how many protons? 6. And neutrons it has 6 as well, right? Now, because it doesn't carry a charge, how many electrons does it have? 6 as well, right? So how many of those 6 can go into the first energy shell? 2. So we can put 2 here, which leaves us with how many? 4. So there would be 4 in the second energy shell. And you always completely fill up one energy shell before you move on to the next. Okay? So this is what a diagram of our carbon atom would look like. Does that make sense? Okay, let's do another. Let's do oxygen over here. Yeah, let's do oxygen. So oxygen has an atomic number of 8, an atomic mass of 16.